Hello guys, welcome on Tesla Adventures. Today in this video, we are going to discuss all the basics of escape velocity and the different types of cases in which escape velocity is used. Now, first of all, let us discuss that escape velocity is also called as second cosmic velocity, and the orbital velocity is called as first cosmic velocity. So first of all, in the question, it can also be named as second cosmic velocity. Now, escape velocity is defined as the minimum velocity required to project any particle out of the influence of gravitational field of the planet or object. So let us suppose that this is a planet, Earth, and we have to project this particle in such a way such that it escapes to infinity. And why we are discussing that it escapes to infinity? Because the gravitational field of Earth vanishes at infinity. So we would be defining escape velocity as the minimum velocity with which it should be projected so that it escapes out of the gravitational field of Earth. Okay, so now we know that initial initial potential energy of this mass on the surface of Earth is ui, and this would be equal to, let's suppose, minus gmm, where m is the mass of Earth, upon r, where r is the radius. And the final potential energy will be zero, obviously, because when this mass will reach infinity, its potential energy will become, the potential energy of the system will become zero. So you can see that the potential energy has increased because this is a negative potential energy and this is zero. So 0 is greater than the negative quantity, so it has increased, and therefore we can say that u of delta u gain, the energy gained, is equal to gmm by r. This is the potential energy gained, and this gain in potential energy will be equal to the loss of potential energy, loss of kinetic energy. So the initial kinetic energy which we have given is half mve square, and we wish to find out the minimum value of ve. So in this case, the minimum word means that we just need to give that much kinetic energy to this mass so that it just reaches the infinity point. And just reaching means that its velocity may become zero at infinity. So the final kinetic energy would be zero. So the loss in kinetic energy will be equal to half mve square, and u gain will be equal to k loss, which is the loss in kinetic energy. So gmm by r will be equal to half mve square, and therefore ve is equal to under root of 2gm by r. This is the escape velocity from the surface of any planet. Now if we see that for Earth, let us discuss that for Earth gm is equal to gr square. So we escape for Earth will be under root of 2gr. What I have done, I have replaced that gm by gr square, so cancelling r with r. So we know that the radius of Earth is 6400 kilometers, and the value of acceleration due to gravity is 9.81. So we can say meters per second square. So we can say that this escape velocity for Earth's surface is 11.2 kilometer per second. So if we project a particle from the surface of Earth in such a way such that there is no atmosphere around the Earth, because obviously we have not considered the atmosphere here, because if there is air, then some part of the kinetic energy would also be lost in the work done against air resistance. In fact, most of the part of the kinetic energy will be lost in work done against the air friction. So you have to give a very high amount of kinetic energy, and in that case, in the case of atmosphere, this escape velocity will be quite higher than this value. Okay, so this is the escape velocity when we are considering that there is no air and there is complete vacuum around the Earth, and then the escape velocity is 11.2 kilometer per second, so that particle does not returns ever. Now we can discuss that the escape velocity is the minimum velocity required to be given to the object so that its total energy becomes zero and it escapes out of the gravitational influence. We know that at infinity, what we have done, that at infinity we know that u final is 0 and k final is 0, which means that total energy of the particle becomes 0. So the particle comes in the neutral equilibrium state, and there is no influence of any force on that particle at infinity. So its total energy would become 0. Okay, so moon, if we talk about the moon, we know that there is no atmosphere around the moon. This is due to the fact that the gases which are situated around the moon have the RMS velocity which is greater than the escape velocity of the moon. So the gases escapes out the moon gravity easily, and the escape velocity on the surface of the moon is 2.38 km per second, and the RMS velocity of the gases near the moon surface is quite higher than this value. Therefore the moon gravity is not enough to bound those molecules of the gases around the moon and to form an atmosphere. So moon does not have its atmosphere, but in case of Earth, as we all know that we have our atmosphere, and therefore we can say that the RMS velocity of oxygen, which is the most required for us to most important for us for breathing, or RMS velocity of other gases such that nitrogen. So the RMS velocity of these gases are these are the most abundant gases of atmosphere. So RMS velocity of these gases is quite low than the escape velocity of Earth's surface. Therefore they are bounded with the planet due to the gravity of the planet. Now it is believed that the gravitational pull of a black hole is so high such that it does not leaves the light also. In fact, light cannot escape the gravity of the moon. In fact, black hole. So black hole has such high gravity such that its escape velocity is greater than the speed of light. So light cannot escape the gravitational pull of that black hole, and therefore any light near that black hole is absorbed in the black hole, and therefore it appears to be black. Okay, and if we know that if the velocity given to the object is less than the escape velocity of that planet, then either that object will fall back on the planet or it will start to orbit around the planet. Okay, now there is an important point about the escape velocity, that escape velocity does not depend on the angle of projection, which means that if we need to project this object from the surface of this planet in such a way such that it does not falls back or does not returns back, so we can project it with at any angle from the surface, because escape velocity will not be dependent on the angle of projection. Okay, so if you project like that, if you project like that, and if you project it like that, then in all three cases the minimum velocity required to be given is escape velocity, which is same. Now escape velocity is also called as second cosmic velocity, we have already discussed, and now let us discuss the third cosmic velocity. So let us imagine that there is a projectile which is projected with a speed which is greater than the escape velocity. Then it is 100% confirmed that it would escape the gravitational pull of that planet, and it would also reach the infinity with some finite velocity. We have already discussed in the escape velocity part that when we are giving this velocity just equal to the escape velocity, its velocity at infinity is just 0. But if now we have given the velocity which is greater than the escape velocity, so it would have some leftover velocity at infinity, and it would move at infinity, or it would maneuver at infinity with that leftover velocity. So that leftover velocity at infinity is called as third cosmic velocity, or interplanetary velocity, or interstellar velocity. Okay, now let us find out that velocity. So let us assume that we have given a velocity which is greater than the escape velocity. So the initial kinetic energy is equal to half mv square, and the change in potential when it would reach the infinity would be g m by r, where r is the radius of this planet and capital M is the mass of this planet. So we know that some part of, and the final kinetic energy is, let's suppose, half m v naught square or v dash square. So obviously some part of the kinetic energy would be converted in potential energy, and therefore we can say that half m v square minus v dash square is equal to g m by r. Cancelling this m with m, this v square minus v dash square is equal to 2gm by r, and v dash square is equal to v square minus 2gm by r. So v dash is equal to under root of v square minus 2gm by r. So this velocity is called as third cosmic velocity. Third cosmic velocity. Or it is also called as interplanetary or interstellar velocity. Okay. Now let us discuss that in this case that there are two planets. You can see that this is one planet and this is another planet. The mass of this planet is m1 and the mass of this planet is m2. The center of mass of these two planets is this one, and this is situated at a distance of r2 from this planet, and this is situated at a distance of r1 from this planet. The distance between the centers of these planets is d, and we need to project a mass m from the center of mass of these two planets in such a way such that it escapes out of the gravity of these two planets. So obviously what we need to do is the fact that the work done by, or work done against gravity, would be equal to m delta v, where m is the mass which is being projected and delta v is the change in potential. So it is m into delta v. Delta v is the potential of infinity minus potential of this point COM. So this is m, and v infinity is 0, and v COM would be equal to minus of gm1 by r1 minus of gm2 by r2. Okay, so the work done against gravity would be, you can see, plus, this is plus of gm1 m by r1 plus gm2 m by r2. Now we know that r1 will be equal to m2 into d upon m1 plus m2. Okay, we know that this center of mass is proportional to the other mass. The distance of the center of mass from the mass 1 R1 is proportional to the other mass, because as this mass would increase, this COM would move towards this mass and R1 will increase. So R1 is proportional to M2. So R1 is this and R2 is M1D upon M1 plus M2. So you can substitute these value here and you can see that it is Gm1m upon R1, which is M2D upon M1 plus M2, plus Gm2m, this is M1 plus M2, and in the denominator it would be M1D. Okay, so work done would be equal to Gm into M1 plus M2 is common and by D is common, so it is M1 by M2 plus M2 by M1. So work done will be equal to Gm M1 plus M2 by M2 M1 into M1 square plus M2 square. Okay, so this is the work done, and this should be equal to half m v escape square. So cancelling m with m, so v escape would be equal to under root of 2 g m1 plus m2 into m1 square plus m2 square divided by, there is a d also, so divided by m1 m2d. So this is the escape velocity in this case. Now in this case, there is a situation in which there is a planet and there is a tunnel which is formed on the diameter of the planet. A mass m, small m, is initially at a distance of x from the center of the planet, and the radius of planet is r, mass of planet is m. Now we need to project this mass in such a way such that it escapes out the gravitational pull of planet. So now in this case, what we need to do is the fact that work done against the gravity will be equal to, again, m delta v, and this is m, and delta v would be v of infinity minus v of this point. Let's suppose this point is P. So the potential of infinity is 0 and the potential of this P point is minus gm by 2r cube into, this is 3x square minus r square. In fact, this is 3r square minus x square. Okay, you can see, if you remember, that this is the gravitational potential of the planet inside a point situated inside the planet, on a point situated inside the planet. So the work done against gravity would be equal to plus gmm by 2r cube into 3r square minus x square. And this work done against the gravity is given in the form of kinetic energy. Cancelling this m with m, 2 with 2, v escape will be equal to under root of gm by r cube 3r square minus x square. This is the escape velocity from a point inside the planet. Okay, so this was complete information about the escape velocity, and always remember that first cosmic velocity is the orbital velocity, which is the velocity with which satellite orbits around the planet, and we would discuss this first cosmic velocity or orbital velocity in the next video. Second cosmic velocity is the escape velocity of that planet. Third cosmic velocity is the interstellar velocity with which that particle which is projected from the surface of the planet maneuvers at infinity. Okay, and the fourth cosmic velocity is till now it is defined as the velocity with which with which we should project that object so that it escapes out the galaxy of us. So this is there are some controversies in the definition of fourth cosmic velocity. So till now it is defined as the velocity required to escape the galaxy of the Earth, which is Milky Way, our galaxy. So this is a controversial, and the definition of first, second, and third cosmic velocities are clearly defined. Thank you.